Hello, everyone. Today we'll explore one of the most fascinating technologies in modern computing, neural networks. Even if you don't have an advanced background in algebra or calculus, don't worry. We'll break it down step by step in a clear and practical way for engineers like you. What is a neural network? At its core, it's a mathematical model that imitates how the human brain processes information. In the brain, billions of neurons work together. Each one receives signals, processes them, and sends outputs to others. A neural network does something similar, but instead of biological signals, it works with numbers. Imagine a grid of connected nodes. Each node acts like a small calculator. It takes some input values, multiplies them by certain weights, adds them together, and passes the result through a special function to decide the output. This happens layer by layer, from input to hidden layers to output, transforming raw data into meaningful results. Layers in a neural network. Think of a neural network as a series of layers, each with its own job. First, the input layer, where the data enters. For example, in handwriting recognition, each pixel of an image could be one input value. Next, the hidden layers, where the real learning happens. Each neuron here combines small patterns from the previous layer, helping the model find relationships in the data. Finally, the output layer, which gives the final prediction, such as this image is the number 7. Every connection between neurons has a weight, which determines how strongly one neuron influences another. These weights are what the network learns during training. How does a neural network learn? Think like an engineer. When you tune a control system, you start with some parameters, measure the error, and then adjust those parameters to minimize that error. A neural network does the same thing. It predicts something, checks how wrong it was, and adjusts its internal weights to reduce the error. This process is called training. The algorithm behind it is known as backpropagation. It figures out how each weight contributed to the total error and how it should be corrected. You don't need the heavy math here. Just remember it's a feedback loop. Predict, measure error, adjust, repeat. This loop runs thousands, sometimes millions of times until the network becomes accurate. Activation functions, the decision makers. After a neuron combines its inputs, it passes the result through an activation function. Think of this as a decision gate. It decides whether the neuron should fire or not, and by how much. Without activation functions, the network would behave like one big linear equation, which limits what it can learn. Activation functions add nonlinearity, allowing the network to handle complex, real-world patterns. Common examples include ReLU, sigmoid, and tan, each with different shapes and uses. Training data and overfitting. Neural networks learn by example. They need large amounts of training data to find reliable patterns. But if they learn too well, they start memorizing instead of generalizing. This is called overfitting. An overfitted model performs great on old data, but poorly on new, unseen cases. Engineers prevent this using techniques like regularization, dropout, and validation sets, which help the network stay flexible and realistic. Why are neural networks so powerful? Because they can automatically learn features that humans use to design manually. For example, in image recognition, early layers detect edges and corners, middle layers identify shapes, and deeper layers recognize full objects like faces or cars. In speech or text, layers learn patterns of sounds, words, and even meanings, step by step. This ability to discover hidden features is what makes deep learning, a special kind of neural network, so revolutionary. Practical engineering examples. Let's connect it to the real world. Engineers use neural networks for predictive maintenance, detecting anomalies in machine data, quality inspection, identifying defects from camera images, network optimization, predicting traffic and load in telecom systems, voice recognition, powering assistants, and call center automation. In all these areas, the network replaces manual, rule-based systems with a data-driven, adaptive approach. Limitations and cautions. Of course, neural networks aren't magic. They require large data sets, computational power, and time, and they can be a bit of a black box. We can't always see why they made a particular decision. That's why engineers often combine them with explainable AI tools or simpler models to make results more transparent. The big picture. If we zoom out, a neural network is simply a pattern recognizer. A pattern recognizer. It takes in data, processes it through layers of weighted connections, and tunes itself until predictions become accurate. It doesn't truly understand the world, but it learns patterns and correlations that humans might miss. And that's incredibly powerful. Closing thoughts. Neural networks are the bridge between engineering and intelligence. They power self-driving cars, smart assistants, fraud detection, and medical imaging. As an engineer, you to master every equation, but understanding how they learn helps you apply them wisely. Use AI not as a mystery, but as a tool for smarter engineering solutions.